All right, we're going to continue with for section 4.3 projectile motion. We're going to be talking about height, maximum height, and horizontal range. So let's share the video. Next slide. Okay, we're going to look at certain conditions of projectile motion. As a special case, really, of projectile motion. We're going to assume that the projectile is launched from the origin at t initial equals 0 with positive vi component in the figure, as shown in the figure, the initial velocity component. And we're going to assume that it returns to the same horizontal level. That's not always the case, but for a lot of cases, it simplifies it if it's the same horizontal level. This is common in sports where baseballs, footballs, and golf balls often land at the same level from which they were launched. In the case of a football, it's not really the case. If something like the punter, his leg is extended, or a quarterback, he's launching from basically the heart, about the top of his head, if his arm is launching the ball from the side of his head. But we can assume in a lot of cases that the start y sub initial equals y final for a lot of these cases, and we're going to make that assumption. Now, so the height of a projectile, there's 2 points that are especially interesting to analyze. The peak point A, shown here in the graph, is at the top of that parabola, and it has coordinates. If the range is r, then at the peak point, the x component is r over 2, and h is the height. And at point B, the coordinates are r and 0. It's come back to it's basically fallen back to the ground. So r is the horizontal range and h is the maximum height. Now, if we find h and r mathematically in terms of v initial, theta initial, and g, we can make some headway. We can make some progress in determining these. We determine h by noting that at the peak v ya, it's equal to 0. In other words, the vertical component of velocity is 0. In other words, when you throw a ball up, it goes up, it stops, and it comes back down. So at the peak, vy is equal to 0 at that point. From a particle under constant acceleration model, that we can determine the time a at which the projectile reaches the peak. The vy final is equal to vy initial minus gt. So the vy final is 0. V initial we get from vi sine theta minus gt. If we solve for t, we can get the time that it takes, and that's vi sine theta over g. Okay. I moved. That's why I wouldn't do it, because there. Okay, substituting for t sub a, which is the time at the peak, and replacing y final equal ya with h, we get the expression for h in terms of the magnitude and direction of the initial velocity vector. So we've got basically we're solving for y final. It's equal to h is equal to vi squared over vi squared times sine squared of theta initial over 2g. That's what all the algebra comes down to. Now the horizontal range From symmetry, the projectile covers the upward part of the trajectory to the top in exactly the same time interval as it requires to come back to the ground from the topmost point. So the range R is equal to the horizontal position of the projectile at twice the time it takes it to reach its peak. So at time TB, which is where it returns to 0, it's equal to 2 times TA, the time it took it to go up all the way up to the top. Using the particle under the constant velocity model with Vx initial equal to Vx B equals Vi cosine theta, and setting x sub b equal to r at t equal to 2ta, we get this equation. The range is equal to 2 Vi squared sine theta cosine theta divided by g. And if we use the double angle formula, you get 2 sine theta I cosine theta I equals 2 sine of 2 theta. We can reduce the range equation to R equals Vi squared sine 2 theta divided by G, and that gives us our range Vi squared divided by G. So it's the maximum value of the range. Note that the maximum value of 2 sine theta equals 1, and sine 2 theta equals 90. So R is a maximum when theta I is equal to 45 degrees. And we'll see that. We'll actually measure that in the projectile experiment that we're going to do in the future. But again, we won't do the projectile experiment until we discuss conservation of energy and conservation of linear momentum. But if we continue on and we look at the trajectories at different angles, you'll see that you'll notice that complementary values of the initial angle theta result in the same value at R. Now, what does that mean? That means that if you fire it at 75 degrees, it'll land at the same spot as if you fired it from 15 degrees. If you fire it from 60 degrees, it lands at the same spot as 30 degrees. And of course, 45 is self-complementary, and the complementary angles add up to 90. So 45 and 45 is 90 degrees. That is the furthest you can go at 45 degrees. If you launch at 45 degrees, now, why is that? Let's discuss that a little bit. If we look at 75 degrees, the vertical velocity is very high and the horizontal velocity isn't. If you were to look at the vertical and horizontal components, the vertical component is pretty long if it's 75 degrees, but the horizontal component is very short. So it spends a lot of time in the air, but it's not going very fast. If you compare that with 15 degrees, it's the vertical component is very small, but the the X component, the horizontal component is very fast. So it's going very rapidly in the X direction, but it doesn't spend that much time in the air. So you end up at the same spot, 75 and 15, the same with 60 and 30 and 45 and 45 and 45 being the longest range. And you can choose 80 and 10. 80 and 10 are complementary. So 80 degrees, it would be shorter than the 75 degree. Anyway, that's the nature of trajectories of projectile motion. Furthest you can get is 45 degrees, and complementary angles land at the same spot. Let's take a quick quiz. Rank the launch angles for the 5 paths in the figure with respect to the time of flight from the shortest time of flight to the longest. Well, it's going to be related to what? How much time it spends in the air. the more time it spends in the air, the higher its flight will be. Well, which one does it spend the least amount of time in the air? Well, the 15 degrees. The vertical component isn't very large, so it spends the least time in the air there, 15 degrees, and the next is 30. So the time in the air would determine the time of flight. So if we rank these, it would just be according to the degrees: 15 degrees, 30 degrees, 45 degrees, 60 degrees, and 75 degrees. The vertical component at 75 degrees is the largest, and so it's going to spend the most time in the air. Okay, let's see. There's I think no, there's two more. Okay, problem solving strategy, projectile motion. You can conceptualize, think about what is going on physically in the problem. Establish a mental representation by imagining the projectile moving along its trajectory. We could categorize this as follows. You confirm that the problem involves particle in free fall and that air resistance is neglected. Select coordinate system with X in the horizontal direction and Y in the vertical direction. Use particle under constant velocity model for X component of motion. Why? Because in the X direction there is no acceleration. And use the particle under constant acceleration model for the Y direction. Why? Because it's always under the influence of gravitational acceleration. In the special case of projectile returning to the same level from which it was launched, we can use these equations. The height is equal to V initial squared times sine squared theta initial divided by 2g, and the range, we can call this the range equation. The range is equal to vi squared times sine 2 theta initial divided by g. Okay, and to analyze the problem, the initial velocity vector is given. We resolve into the x and y components. We select the appropriate equations from particle under constant acceleration model for vertical motion. Use these along with the top equation for horizontal motion to solve for the unknowns. You finalize by, once you determine the result, check to see if the answers are consistent with mental and pictorial representations and the results are realistic. Okay, now that we've discussed the problem-solving strategies, we will next discuss some example problems. We're going to end the video now. We'll pick that up in the next video so that these videos don't get too long.